function 2. Okay, find the integral. So part A, find the integral of this function here. So 24x squared times x cubed minus 8 to the power of 3 dx. So you notice here that it's a product of two functions, so you can't necessarily integrate this easily, so you do a u substitution. And you're going to substitute the function that is inside of the brackets, because that's the most complicated part. And also noting that if you substitute this part out, remember that when you do a u sub, you also have to differentiate the u sub to get rid of the dx to integrate in the u world. And the differential of x cubed minus 8 differentiates to x squared. Well, specifically 3x squared, but basically the power reduces down from 3 to 2. So the suitable substitution would be substituting out x cubed minus 8. So let u equal x cubed minus 8. So du over dx is equal to 3x squared. Or in other words, dx, when you rearrange for it, is going to be du over 3x squared. So then we can transform our integral into the integral of 24x squared times x cubed minus 8 turns into u, and then cubed, and then dx turns into du over 3x squared. You'll notice that the x squareds, they cancel each other out, and the 3 and the 24 cancel out to 8. And so what I'm integrating now is just the integral of 8u cubed du, which then gives me 8u to the power of 4 over 4 plus c, and the 8 and the 4 cancels out to 2. And then we know that u was originally x cubed minus 8, so x cubed minus 8 to the power of 4, and then plus c. I think that's a very inappropriate achieved question, considering you have to do that, or you have to use the reverse chain rule. Anyways, that doesn't matter. Part B seems like it is a numerical question, which I'm actually not that bothered to do, so I'm going to skip across that. But you just use Simpson's or trapezium rule, it seems like. But yeah. Okay, let's go on to part C. Okay, so given that dy over dx equals 2x plus 1 over y, and given the points that y equals 2 when x equals 1, so those are coordinates when you're solving your differential equation, because you always, whenever you integrate, you get a plus c, and you're using a point to solve for that plus c. Find the value of dy over dx when x equals 3. Okay, so obviously you can't know the value of dy over dx when x equals 3, because you only know the x value, not the y value there. So you need to solve for a y equation. So you're going to separate your variables, because your variables are together right now. So y needs to go over there, and then dx needs to go over there. So you're going to multiply both sides by y and then dx. So the dx's cancel over here, and then the y's cancel over here. So then you're integrating y dy, and then 2x plus 1 dx. So the left-hand side becomes y squared over 2, and the right-hand side it becomes 2x squared over 2 plus x, and then plus c. Only one plus c is necessary. And we know that the point y equals 2 when x equals 1 exists. So you're going to let y equal 2. So this is 2 squared over 2 is equal to 2 times 1 squared over 2, and then plus 1, and then plus c. So this 2 squared over 2, one of the 2's cancel each other out, so it's just 2. This 2 over here cancels out with this 2, and then 1 squared is just 1. So this is 2 equals 1 plus 1 is 2 plus c. So c is equal to 0. So your y, particular solution to this differential equation is y squared over 2 is equal to, well, the 2x squared over 2, the 2's actually cancel each other out. So it's just x squared plus x. And we want to know what the dy over dx value is when x equals 3. So we want to solve for what y value occurs when x equals 3. So let's solve for that. Y squared over 2 is equal to 3 squared plus 3, which is just 12. And then solving for y is equal to the square root of 24. And you can leave like that, or you can leave it as 2 root 6. Okay, so we know the y value, so then we can substitute both x equals 3 and y equals 2 root 6 into the dy over dx original equation. So we know that dy over dx was originally equal to 2x plus 1 over y. So then now we know that it's going to be when x equals 3, so that it would be 6 plus 1 over y, which is 2 root 6, which is then 7 over 2 root 6. And that is the answer. Okay, on to part D. Find the integral of, so this is the integral of x over square root x minus 5. And the substitution of u equals x minus 5 may be useful. Okay, well that makes sense. Okay, so you're substituting out a linear factor. So let's see when u equals x minus 5. Again, you need to differentiate this. So du is equal to, well, x just differentiates to 1. So then it just is du equals dx. So you can make a simple substitution. So if u equals x minus 5, then by rearranging this, x is equal to u plus 5. So then when you rewrite your integral, this is the integral of x, which was u plus 5, over square root of x minus 5, which is now u, and then dx can be substituted out with du. So now you have here the integral of u over square root u plus 5 over square root u, which you can then, du, rewrite, because this is a power of 1 and then this is a power of 1/2. So then by fraction rules, you know that this is just u to the power of 1 minus 1/2, which is just square root u. And then the other one you can bring up as u to the power of negative 1/2. So let's rewrite that root u also as to the power of 1/2. And then we can integrate this. So you add 1 to the power, u to the power of 3 over 2, and then divide by the new power. And for the next one as well, add 1 to the power, and then divide by the new power. And then there is a plus c as well. And we know that u was equal to x minus 5. So this is 2 bracket x minus 5 to the power of 3 over 2 over 3 plus 5 x minus 5 to the power of 1/2, which is just square root, but we can just leave it like this. And dividing by half is multiplying by 2, so then this should become 10, and then plus c. So that's your answer. Okay, and then part E, which is apparently scary, so I'll brace myself. Okay, the graph shows y equals x times k minus x, and y equals mx, okay? And the shaded area bounded by the functions y equals x, k minus x, and y equals mx is equal to the unshaded area bounded by the x-axis and the two functions. The point of intersection of the two functions are at 0, 0, and k minus m, k minus m. Prove that the gradient of the linear function is exactly m equals k1 minus 1 over cube root 2. Okay. Sure. Okay, so what I'm going to do is, so this is what the graph looks like, right? And we know that this point of intersection is at k minus m, and then m bracket k minus m. And we know that the first area is equal to the second area, and the two functions are y equals mx, and then y equals to x bracket k minus x. So we can kind of calculate the area or find an expression for the first area and the second area, and then solve for the m value that exists here. And the area of the first function, or the first part over there, let's see. So for the first part, the area between curves is, again, the area from point A to B of the top function minus the bottom function. So the top function in this case, well, your limits of integration are from 0 to then k minus m. That's the x coordinate, so k minus m, and then this part over here being 0. And the top function here is the quadratic, the x bracket k minus x. And the bottom function is the mx. So then integrate, so then I can kind of expand all this out. So 0 to k minus m of kx minus x squared minus mx dx. And the x components, you can kind of factorize out x here. So 0 to k minus m of negative x squared, and then plus x times k minus m dx. So then integrating this gives me negative x cubed over 3, and then plus x squared over 2, and then it's still multiplied by k minus m because that's a constant that doesn't change. So 0 to k minus m. And then substituting in k minus m and 0, well, we don't have to worry about the one about 0 because when 0 is applied to both of these expressions here, it just goes to 0. So we're only interested in the k minus m component. So this is negative k minus m cubed over 3 plus, and then notice here that k minus m and then k minus m squared is going to give you as well k minus m cubed, but that's over 2. So you can simplify your expression here by cross-multiplying the denominators so you can add the two fractions together. So you're going to multiply the left-hand side by 2 over 2 and the right-hand fraction by 3 over 3. And what you're left with is negative 2 k minus m cubed plus 3k minus m cubed over 6, which then gives you positive k minus m cubed because it's just negative 2 plus 3 essentially, and then over 6. So we can simplify that expression quite far. And so that's the first area. And then the second area is going to be... So when I look at the second area, I'm thinking about how I'm going to go about this, because usually you would think about doing the top function minus the bottom function. But if you see here, if you were to separate out this point here, you can see that the area bound here is, one part is a right angle triangle bounded by the linear graph, which actually isn't an area between curves. It's just the area underneath that curve. And then this area over here is just the area underneath the parabola. So this is, the red shaded bit is going to use integration, but the area underneath the linear graph is just going to be a right angle triangle. Area equals half base times height. So let's label this 2a and this one 2b. So in the area of 2a, that's going to be equal to, well, if we draw out the triangle, that's a horrible triangle. This is going to go across from, so the base is from 0, it starts at 0, and then the x-coordinate is k minus m. So this is simply just a length of k minus m. And then the height of it is just the y-coordinate, which is the m, k minus m. So then the area of this is going to be half of base times height. The base is k minus m, and the height is m times k minus m. So then this gives you m over 2 times k minus m squared. Okay, so that's the first part of 2. And then 2b is going to be the integral from, well, the x-coordinate of the point of intersection here is going to be still at k minus m. And then what about this point over here? Well, this point is the x-intercept of the parabola, or the second part. And if you look here at the parabola, the points of intersection are going to be at 0 and k. So this is at k over here. So your limits of integration are from k minus m to k. So k minus m to k of just the parabola. We're not interested in the linear line because it's not involved in this one here. This will be x times k minus x dx, which you can expand out as xk minus x squared dx. Integrating this will give you x squared k over x minus x cubed over 3 from k minus m to k. So your k minus m expression is going to be, sorry, that should say over 2, not over x. it's going to be k minus m, sorry, wrong way around. It's going to be, well, if you let x equals k, you got x squared times k, which is just x cubed. So, sorry, k cubed over 2, and then minus k cubed over 3. And then you're going to be minusing off, and x squared equals k minus m. You got k minus m squared times k over 2, and then minus k minus m cubed over 3. Okay, you can kind of simplify this expression over here by using fraction rule. So you're going to multiply this side by 3 over 3, multiplying this side by 2 over 2, and then to make the denominators the same. So this will be 3k cubed minus 2k cubed over 6, which gives you just k cubed over 6. And the other expression, you can factorize out k minus m squared. So k minus m squared. And then left in the brackets, you're just left with k over 2 minus k minus m over 3, which you can, again, join the fractions together by multiplying this by 2 over 2, multiplying this by 3 over 3. And what you're left with is k cubed over 6 minus k minus m squared multiplied by 3k minus 2 times k minus m over 6, which we should simplify a little bit. So just going over to a second page. To be continued. What was that? K to the power 3 over 6 minus k minus m squared bracket 3k minus 2 bracket k minus m over 6. Okay, so let's simplify this. K cubed over 6 minus k minus m squared. So the 3k, and then when you expand out this bracket, you get 2k, negative 2k, and then positive 2m. So then this gives you 3k minus 2k just gives you k, and then plus 2m, and then over 6. And all of this is over 6, so you can combine all of the fractions together. So k cubed minus k minus m squared times k plus 2m, all over 6. And we know that these two areas are equal to each other. So we can set the area of the first one. Oh, sorry, we need to combine the two areas together now. So the total area of the second portion is going to be the first part, which is k cubed minus k minus m squared times k plus 2m over 6, adding on to the second component, which is m over 2 times k minus m. So m over 2 times k minus m squared. Okay, we should probably join these fractions together. So you're going to multiply this by 3 over 3. So I'm left with k cubed minus k minus m squared times k plus 2m plus 3m times k minus m squared all over 6. Okay, it's getting very messy. You should notice that if you were to multiply out this component, the 2m, what you'll get here is k cubed minus k times k minus m squared minus 2m times k minus m squared. Right, that's just expanding out those brackets there, but not the k minus m squared brackets. And then you're adding on 3m times k minus m squared over 6. You'll notice that these m times k minus m squared are like factors or like terms. So you can simplify this to k cubed minus k times k minus m squared plus m times k minus m squared, which you get then, okay, and that's all over 6. And then you can factorize out the k minus m squared there. So k cubed plus k minus m squared, and that gives you m minus k. But if you have m minus k, you can then multiply this by -1. You can multiply this by -1 to flip the sign of this to be k minus m, but you need to multiply this by -1 here to reverse this. So what you have is just k minus m squared times k minus m, which is just k minus n cubed. So k cubed minus k minus m cubed all over 6. So we've reduced down that horrible expression down to k cubed minus k minus m cubed over 6. And if you do expand this out, you should notice as well that the k cubed that results from both of them will cancel each other out. But let's not worry about that right now and equate the two areas together. So initially, the first area is k minus... Okay, so area 1 must equal to area 2. So the first area was k minus m cubed over 6. And this should equal to k cubed minus k minus m cubed over 6. Okay, and we can see that there's 6 on both sides. We can cancel them out. And you'll see here that you got negative km cubed, negative k minus m cubed. And you can move that to the other side and become 2 lots of k minus m cubed is equal to k cubed. In order to get rid of the... So we need to solve for m. The whole goal of this is to solve for m. So we need to free up the m from there. So we can divide both sides by 2. And you'll have k minus m cubed is equal to k cubed over 2. And we can take the cube root on both sides. And what you're left with is k minus m is equal to, well, the cube root of k is just k, and then over the cube root of 2, which we don't know, which you can just leave it as cube root of 2. And then you're going to take the k to the other side, so k over cube root 2 minus k, and you can divide both sides by -1 to free the m over there. And you can also take out a factor of k here, so you can factorize this as k times 1 over cube root 2 minus 1, and you're dividing both sides by -1, you get m equals to negative k times 1 over cube root of 2 minus 1. And when you have a negative, you can factor in you can expand the negative into the bracket to reverse the signs in there. So you have k times 1 minus 1 over cube root 2. And I think that's the form they wanted. Let me just double check. It is. Okay. So that's your answer. My days, you are right. That was pretty difficult. Well, we got there in the end. I hope that kind of makes sense. Like, this is my first time doing it as well, so I hope I explained it well. If not, definitely do ask. That was hard though.